Physics Unit 4, Capacitor Charging and Discharging. In this video, we are going to looking at the content of your textbook, Chapter 6b, page 46 to 51, and the spec points 4.4, 104 to 104. Charging and discharging circuit. Charging and discharging circuit. So here is the circuit given. Now when the switch connected to at A, it is the charging circuit. It's charged through the battery from the what we call the power supply, and the capacitor is there with the capacitance of 100 microfarad. So you can investigate how the current through the capacitor change over time by connecting to data logger and the current sensor. So if you want to see how the voltage also vary, you can add a voltmeter or voltage sensor parallel to the capacitor. If the capacitor is fully charged, it will charge up to 6 volt. We have learned that in the capacitor basics, and we can, from the equation Q equals CV, we can calculate how much charge it's there, and then you can work out. If you go to this example, you will get 0.6 millicoulomb charge. Now in this charging circuit, what happened? The electrons are influenced by the electric field of the potential difference. That is, potential difference is the electric field there to supply voltage. Then under the influence of the electric field from the power supply, the electrons move from negative end of the battery to this plate. Then this plate will get negative, and this plate will get positive. So electrons move through the outer circuit, right? So it's there and drag from this and bring it here. So this plate become positive, this plate become negative, right? So when it comes to the discharging, we'll see what's going to happen. Now when it's switch turn to this point at B, so then the capacitor start to discharge. As the capacitor discharges, what happened? The current starts at the beginning. The current starts at its maximum because the potential difference is there fully, which is equal to the potential difference of the supply. So we can calculate. If you want, we can calculate the current at the beginning, because it's the charge. The capacitor is with full of charges. It's like the bottle, your drink bottle is full with water. So you can get the maximum out. So here the maximum out, you get the electron flow. Like water, you get electron flow, and that is the flow with time of electrons. We call the current. So you get the current, maximum current. You can calculate the maximum current that you get by using the Ohm's law. That is the potential difference divided by the resistance. So you get the current as 0.06 at the beginning, right? So when the electron flow out from the capacitor, or the charge flow out from the capacitor, what we call the discharging capacitor, PD, potential difference across the capacitor, get reduced, and the electric field is reduced, and the push on the electrons by the capacitor as like a battery, so it get weaker, right? It get weaker. So when it get fully discharged, what happened? When it get fully discharged and no more charge to flow, so no more current, right? So current will fall to 0. This is what happened in charging. When it fully charged, at the beginning the large current passed through, as the potential difference is maximum across the resistor, so then it decreases, current decreases. As it fully charged, the no potential difference across the resistance in the circuit, and the capacitor obtained the total potential difference, so the current will not flow, it comes to zero. Then when it starts to discharge, the direction is opposite. You have to understand that direction is opposite here. But that direction opposite idea you get here, when it's charging, this get negative, as this is negative and this is positive, so this get positively charged. So as we mark, the current enters in charging, the current enters like this. So this C is for charging, current enters, and current enters this thing. Actually the electrons, right? This electron. So this is when it is connected to this position. So this is the positive plate. So start the current from this way. Actually the current electrons is moving other way, so the current is on this way. So the discharging, I mark discharging current as DC, IDC opposite. So charging when it is this way and discharging other way. That's the point you have to understand, how this discharging current become negative. That is not negative, it's actually the opposite. The idea of opposite, it become negative. Earlier positive and discharging is negative, and it's the pattern, right? So same way the voltage, capacitor voltage at 0, then increase up to the supply voltage, and when it's about to discharge, starting with the supply voltage and decrease, and charging, and the voltage is pattern will be the same. How could we make the lamp there? Here the lamp. How could you make the lamp to light more duration? So that we can have two possibilities, that is to store more charge on the capacitor and decrease the rate which capacitor discharge. The rate of charge flowing outside the capacitor, we have to decrease. The rate we have to decrease. We have to release it more slowly. How to do that? Then let's look into it. Now when we have the same maximum PD, so if we increase the capacitance, then the initial charge that the capacitor holds will be more. So same PD, but we are going to have a capacitance with large capacitance of the capacitor. Then when the charge flow out in discharging, so if you want to make it more slow, so then electrons flow, then what we have to do, increase the resistance in the discharging circuit. So then that is R. So when we increase the R, so it will flow more slowly. So then what are the two things that we consider to increase the time of discharging is C, capacitance, R, the resistance of the discharging circuit. So these two join together to make the fact rate of discharge of a capacitor. So that's what we call these two together the time constant, right? Time constant, time of the rate of discharge depend on capacitance of the capacitor and resistance of the discharging circuit. So we denote this time constant by the letter called tau. So tau equal RC, or just you can remember it as the time constant. Here the resistance should be in ohms and capacitance should be in farads. So the total together time constant, we will get it as in seconds. So this gives, time constant gives an idea how many seconds it takes for the current to fall 37% of the starting value. So don't worry, we will look into that later in this video, how this 37% comes out, right? So this is the same scenario is used for the courtesy light in the car, that is with the discharging capacitor. So when we manipulate the R resistance of the discharging circuit, you can understand that the time it takes to discharge fully will be longer, right? So you can read the text and get more detail, but firmly you have to get the idea. So the idea of time constant has manipulated or altered in the way that we want to have the long time discharging for the capacitor. So let's work out a time constant for a circuit. Now here for this circuit, time constant is RC. R is the resistance of the discharging circuit, that is 100 ohms and 100 microfarad. So you get 0.01, the discharging circuit, the time constant. So it's very short time. So you can say that it's a flash on and off. So quickly we could not spot even a time constant like this, right? Okay. So discharging capacitor, right? Discharging capacitor maths, when we think of the mathematics side of the discharging, so the graph that we have seen is curves. These curves are known as exponential curves. What do you mean by exponential? Is equal change in equal time intervals. Equal change in equal time intervals, right? So for the capacitor discharging, we have a relationship like this. This exponential relationship. This is the charge now. This is the initial charge, and the time t is the time take for this initial charge to fall to present charge, and this e to the power minus t, the time is q0 to fall q, the time taken, and it's over time constant. So time in seconds, time constant in seconds, so no problem with the units. So it will cancel out, then only a figure will be there. So let's see how this works. Now take this example, right? Take this example. First of all, then we are substituting to work out the charge remain. Charge remain is the Q here, right? That's what we want to find. So it's a problem for us. And the initial charge we have not given. So we can calculate, because the capacitance of the capacitor is 0.03 farad. So here it is farad, but if it is not in farad, you have to convert it to farad. So it is there, right? This is the C, and V is the supply voltage. So we have that also. So then we can calculate the initial charge. So this is okay, and is connected to discharge through 900 ohm resistor. So then this R is known, capacitance is known. So this substitute, right? After 20 seconds, so this is the time taken, right? Time taken, how the 0.36 charge fall to Q. So then that is also known. So we can calculate this finally. So as is the first example, I work out with much slowly to understand. Identifying the figures. First you have to know the relationship, then identify the figures given and substitute carefully with units. Then you will have no problem in that. So when it comes to the same scenario, the discharging circuit, we have mainly identify this as for the discharging charges, right? So here if we substitute Q with CV and Q0 with CV0, V0 is the initial potential difference and initial charge. So when we substitute that, this get cancelled, you get this equation, right? So it can be work out like that, simple manner. So this is another example working out for you to understand the relationship. So as we did earlier, what you have to do, is to identify the figures given and substitute to the equation carefully, and then you can get the answer. So as we know that the relationship of V equal IR, and we can substitute V, replace V by IR. So present potential difference is IR, and initial potential difference is that the supply voltage is I0R. So when we substitute that as previously, the R is constant, so R get cancelled, so you get the relationship like this. So this is the graph for this discharging. So this is what we call exponential curve. So working for the relationship, so you have to understand how you identify the quantities given. Here the initial current you have to work out, it's not given. So from the provided information you have to work out that. So voltage is given, resistance of the discharging circuit is given, so you can get the initial current, and with the initial current other things have been there, the provided information, you have to grab it. Now in the exam also, you better to follow my method to underline or circle it the figures that's given for you. Then you can easily track out what is not given and what you should calculate initially and what is the final destination of the answer. So charging and discharging circuit, we have to understand. I have explained earlier also, but better to understand in this way. Now when charging, the supply voltage is applied across the resistor and the capacitance, right? So capacitor, right? Capacitor and the resistor. So capacitor and the resistor is in series. So potential difference of the supply is shared by these two. So that's what I have written here. Supply voltage is equal capacitor voltage or PD and the PD across resistor. Now when we charge, what happens? When the plates get charged, the potential difference between the plates increases. Then the resistor, the potential difference across the resistor decrease. So that's why the current decrease, right? Because initially the large current pass as the whole potential of the supply is applied across the resistor. But when the potential difference across the resistor decrease, what happens? The current decreases. So when it fully charged, the whole potential difference is applied across the capacitor. Then the resistor, across the resistor, the potential difference will be 0. So that's what we call supply voltage will be equal to the potential difference of capacitor. Now I have introduced the word exponential curve. Exponential, I told that it is the equal change in equal time interval. So let's have the information, right? For this, the graph showing exponential decay of the ratios, right? Values n after successive equal time intervals, very important, successive equal time intervals, how the n varies. So these are the figures. So time intervals 0, 10, 20, 30, 40, 50, and the n values 4, 2.5, 1.6, like that. So the ratios, successive values in n, right, we can give it now 4 over 2.5, then 2.5 over 1.6, 1.6 over 1, 1 over 0.6 and 0.6 over 1. So you get the ratios for the successive values of successive time intervals. So then you can see the values that is obtained, right? So this is same, right? The ratios are same, right? Almost same. This is close, right? And the curve shows, we can say that curve shows exponential decay or exponential. That's how we identify the whether the curve is an exponential curve. So better to remember this. If you are given a situation to show that the curve is exponential, you have to use this method to show that. So let's examine the time constant a little bit more detail, right? Time constant RC is the time that takes the charge, voltage and current falls to 37%. That's how we describe initially also. So let's see how quickly the charge capacitor discharge. So this is the relationship. So if the time taken is equal to RC, so I told that RC is a time, that's what we call time constant in seconds, right? So the time, this time T is the time taken for the charge Q0 to fall Q. So the time taken is when the time is equal to the time constant. So then this get cancel out is not become 0, it become 1, minus 1. So the ln minus 1 is given 0.366666. So we can round it off for two significant figure, that is as 0.37. So that's how this 37% came. That's how 37% came. Now 37% is the remaining. So how much discharge is the other way? That is 63% have discharge from the original value. Decrease amount is 63 and remaining is 37, right? So better to remember that when the capacitor is fully discharged, it takes approximately 5 RCs. If it is total charging and discharging, then you can see that, you can understand that it is approximately 10 RC. Charging 5 RC, discharging 5 RC, together 10 RCs are going. So this is another relationship. We will work out how it can be obtained, right? And look at this graph. So let's think that it is 100 at the beginning. So one time constant, it falls to 37. Then next time constant, 37 from this 37. Then you can calculate and see when you multiply 37 multiplied by 0.37, you get this value. And when you multiply 13.7 from by 0.37 again, so this is the 37% of 100. This is the 37% of 37. This is the 37% of 13.7. This is the 37% of 5.07, like that. So equal, that's what the meaning. Equal change is 37%, falling to 37%, or discharging 63%, time interval will be the same. So that is the basic feature of the exponential curve. So this is how we can see the units of the RC. I have told you that R should be in ohms and capacitance should be in farad. So ohm is V over A, that is voltage over current. So when we substitute the units, and farad, the capacitance is charge over voltage. So capacitance charge is coulomb over volt get cancelled, then we get coulomb over ampere. Then charge is Q equal IT, I is A, T is seconds, so AS and AA cancel, you get finally the seconds as the unit of time constant. So expression for RC ln2, I have told that I have promised you to discuss that matter a little later. Now let's see. So if time taken to Q0 to become half of that, if the time is half T, what is half T? The initial charge to become half. Initial charge to become half is the T half. So this is the relationship, and if you get down this is the fraction, the present charge as a fraction of initial charge. So you get this. So we can work out this is half then, because I have given this is the time T half is to become half. So here I have not put T half, it should be now from here it's T half. Let's put it that there. Now here onwards it's T half, right? I have not put it there as T half. It's become complicated, so it's actually the T half is there. Then so I can work out as ln both side, ln, make it ln, then ln half is equal minus T over RC. So then I can write this here, T to the power 2 to the power 1, then when it comes up, T to the power minus 1, and here minus minus get cancelled, then we get, and cross multiply RC ln 2 equal T half. This is a T half there. So a good relationship to keep in mind. You have to you can work out for your calculations, and remember this is same as, now you know that charge and behavior of charge in discharging and voltage and current in the same pattern. So same thing, to current to half, charge to half, voltage to half, this is the relationship. There is a relationship with RC with ln2, right? So let's move to the practical that display and analyze the potential difference across the capacitor as discharged through resistor. So we have to measure in this practical, but we have to measure the time constant for the discharge. For you know that time constant is RC, so you need to measure R and the capacitance. So you can get that, right? If you know the resistance and if you know the capacitance of the capacitor, so that is RC. So observe the effect of charging values of the resistor. Now with the resistor, as we discussed, we know that we can increase the time, we can change the time constant of the discharging circuit, and thereby we can delay the charge, or we can short the discharging period. Increase, make it longer or make it shorter, right? So to measuring the time constant, we can use the multimeter to measure the value of the resistor, and using the oscilloscope we can measure the value for the EMF of the battery, or the voltage of the battery. So here one example picture of oscilloscope, how it display the voltage. So you can get the divisions. You can get the division one from the peak to peak, 1 2 3 4 5 5.6, the halfway. So get the divisions, right? Division. Now here it displays 1 volt per division. It is fixed like that here. Then you can get the voltage, right? Then we can set up the circuit like this, right? And oscilloscope as the voltmeter, as I showed. So you can measure the voltage and with the time, right? Okay. So then we can have the voltage and time readings, right? Voltage and time reading. So in discharging process, right? So when we fix the switch there, at that instance we have to start the stop clock. So we can use the lap timer facility to record with the known values, right? When it falls to 5 the time, 4 the time, and 3.5 the time, right? That is one way. If it is so fast, what we can do, always fully charge and discharge to the time taken to discharge to the particular value. There is another method that we can follow, right? If it is quickly discharging, right? So we have to repeat then to get the values. So somehow we have to have voltage values and the time values for taken to fall the voltage to that particular voltage, right? If you have a sufficient readings, then we can plot a graph, right? Plot a graph of voltage and time. So from that we can calculate the time constant. Now say like this is the graph, okay? So this is the curve that we obtain, right? This is the value. So this is, say it is 100 for example, right? Here it is 6.1, right? It is 100. So then we have to calculate the 37 of this, 37 of this is 37. Then at that time how it crossed the graph and get the time. So this is the time value. So this time value is the RC value, right? Then you can use a graph paper and plot this and get the time constant around 50.5. and if you know the RC as R is given, you can calculate the capacitance of the capacitor. So that is, you should get somewhere around this, right? So this is a homework for you to work it out by your own, right? And this graph, this for this third question, right? Figure 2.21 is the for that, right? And then you can further, I have included 5 questions for you to do as homework, and I have included some links for you to go and watch, right? And that's all. So that's the end. So I hope that you have got a brief and good idea about charging and discharging and the capacitor mathematics, right? And what is exponential all. So let's meet again from another video. Till then, goodbye.